He works for Eventbrite as architect, helping to scale things up. He is also a Django core developer and creator of South Migrations. And he will talk about systems where big data doesn't apply. Small data storage for the rest of us, Andrew Godwin.
Thank you. So, hi everybody. As has been implied, I'm here not to talk about big data, but about small data. Now, first of all, a brief introduction to myself. I'm Andrew Godwin. As said, I'm a Django core developer. I was involved a lot in the new Django migrations for 1.7, if you're familiar, and with South migrations previously. And I'm a senior engineer at Eventbrite. I handle sort of a lot of our architectural and design stuff there. I also have too many hobbies, but there's not enough time for that, so let's go on. Big data, what does it mean? Now, to different people, it has different meanings, but you hear a lot, especially in the industry, especially in news, we have to deal with big data. And my question to you is, what is big? Is it 1,000 rows? Is it 1,000,000 rows? Is it 1 billion? Is it 1 trillion rows? And to different people, each of these answers is yes, that is big. And so you have to work out exactly where you sit, and I bet you anything that 95% or 99% probably of you in this room don't have what at least I class as big data. And actually, you're better off designing smaller systems and leaving the scaling till later. Scalable designs are always a trade-off. They sound fantastic. They're really fun to engineer. Like, there's nothing better than spending, a few months making a perfect scalable system. But what you're doing is spending all this time now when you could be developing your product instead, or fixing bugs, or doing other things. And what you're actually doing is making an overcomplicated system. And that can end up making it slower and slower in the future as you've got to adapt to this huge enterprise-ready system that you just don't need yet. Like, you've made your life much more complicated. If you're a small company or an agency especially, so I used to work at an agency and at a small startup. Both of these kind of companies do not require big data. What they need is small, agile data. And the word agile here is perhaps overused, but it's the idea of this sort of like, you need databases that change fast, that you can deploy to quickly, that can change with requirements as your product evolves or your project evolves. And you don't need to scale from scale one. But what I'm here to do is not just to tell you, don't scale. I'm here to tell you how to do it intelligently, how to design a small system up front that you can leave the right breakpoints in, that when you have to scale, you know and you have a plan and go, okay, this is where we're going to do it, and this is how, and we have this game plan, as it were, to take us from small to big without any extra effort. And this is what a lot of architecture is about, especially in my role at Eventbrite. It's, well, we know we need to scale eventually. We just have to work out where we can leave gaps and where we have to do work up front. Leave those gaps, do the work we need to, and then later on we can come and fill in the holes and make it much better. So there's 4 things I want to go over here as sort of basic advice. And then later on in the presentation, I'll show you some interesting sort of storage challenges that I like to sort of show about and disseminate. But first of all is rapid development. Now, this is a topic close to my heart. I have been involved with writing migration systems for about 9 years now, which is about 8 years too long, perhaps. But it's all about schema change. Now, one of the things you never know going into a brand new project is what your schema will be. If you do, congratulations, you are very, very rare. What you end up doing is you go into the project full pelt, and then requirements change, new things come in, new features happen, you find out things you want to add or you didn't even know you wanted. And if you have this schema fixed in time, that's basically impossible. And so it's very important that going in, you have flexible schema. Now, this can be one of 2 things. It can be a flexible explicit schema, which for most of you will be a relational database like Postgres or MySQL, or it can be an implicit schema, like a document store such as, say, CouchDB or MongoDB. Both of these have their advantages. In particular, the implicit schema does not require alteration at runtime, but do bear in mind that you're not eliminating schema versioning with implicit schema, you're moving it into code. In particular, you have this problem where if you change an implicit schema over time in documents, you end up with subtly different versions of the document. And you still need migrations. If I change, for example, you can see here, this weight field here is an integer of 74, and over here is a string of 85 kg. Now, it could be I've changed the kind of this field from integer to string in my code, but every time I do a change like this, I have to go and write if statements and make my code go, well, okay, if you see an integer here, decode it like this. If you see a string here, decode it like this. And again, you see, like perhaps here I've got a mistake with my translation thing. I've put the French nom there rather than name. And all these sort of subtle issues can come in, and your database won't catch any of those for you. You're responsible now for the code that validates, the code that does versioning, and if you're doing it correctly, every time you make this kind of change, you should write a script that goes through every single document and updates all the documents to match the new format. That is not what this slide is meant to say. Okay, well, we'll skip over that one. What the slide was saying was, I'll go back and show you here we are. The slide is meant to say continuous deployment. Apparently it doesn't today. So the idea behind continuous deployment is having a database that you don't need to take down when you're changing the schema. So it kind of ties into that previous point. So most databases, okay, see, MySQL, in fact, whenever you change something, especially in 5.5 and below, it tends to lock the entire database. And for example, at Eventbrite, we have a very, very large database. Adding a column to some of our tables can take over a day. And so we do not want to stop the site for a day to add columns. That's considered not good by the business. So what we want to do instead is add this stuff sort of silently in the background. And what's one of the good things about this is in most databases, including MySQL 5.6, if you add nullable columns, that's free and instantaneous. So Postgres and MySQL 5.6 in particular. And then while you can't add defaults, because adding defaults immediately jumps to it has to fill in every single row in storage and takes forever, you can add this and then slowly backfill over time, over a day, over 2 days, and then leave your code that uses that column not deploy for now, have the database updating itself, and then in parallel it gets there, new column, fully populated, fantastic, deploy the new code, everyone's happy. Similarly, one-to-one relations, you can do the same kind of thing. You can slowly add them or slowly split up tables. Just always think in sort of phases. The idea that you want to deploy some initial code first that perhaps supports making the change, make the change slowly, then finally deploy the code that uses the change. So usually it's make a new table, migrate data into it, and then use the new table, or similar things like that. Finally, one important thing at the bottom there is certain changes of type are natively supported by your database, and they're a lot faster than doing them yourself. One example of this is we wrote a MySQL to Postgres converter at Lanyard, one of my old companies. And initially, we read every single row from the database in MySQL into Python, translated the types, and pushed it into Postgres. This, as you can imagine, is incredibly slow. But what we ended up doing is making an exact copy of the MySQL schema in Postgres. So for example, Django uses tiny int for Boolean, whereas in Postgres it uses bool. But Postgres is a superset of types. So we took the schema exactly, put it in, and then just told Postgres, change this column to this type, and it did it in like a minute. Like, it's so much faster and so much quicker at that. So be aware of what your database can do, especially with that kind of type change, and use it to its advantage. Hardware choice, this is very important. Now, a lot of startups, correctly, because they don't have much capital or money, go for the cloud. The cloud is very expensive. I can tell you this now, most companies will save money by moving to hardware if they have enough ops talent. The cost is always having people who can do ops on those servers. But at some point, you'll end up with it. And in fact, at a previous hosting company I ran, we cut our bills by half by moving to physical servers. Unusual case, but it is the case. But there are other things of the cloud that are an issue. And you probably should choose it, but I want to make you aware of why you should think for a little bit what you're doing. So first of all, virtual machines are absolutely terrible at I/O. We've fixed things like memory access, we've fixed things like CPU virtualization, but the I/O is still not great. There are virtualization things for I/O. They're not brilliant still. They're getting better, so hopefully one day we'll be there. One case of this is not true is things like Docker, which are containers, because they're not virtualization. So those are at least as natively fast as the machine they're running on. So these days, perhaps having a colo that's bare metal and Docker on it could be considered much more viable than, say, having a virtual machine and putting something else on that. Memory is king. In particular, I've seen people cram their database on machines with all of their other stuff. So, oh yeah, we have Postgres and Redis, and we have Elasticsearch on this machine, and we also have the web server, and we also have, like, you know, Bob's personal homepage over here, and it's just, no. Databases really love memory, and they really love having lots of spare cache for that memory. So what you want to make sure is that you go in and give the database its own server with plenty of memory, and it'll be a much happier thing. Just having one other thing on that machine that's memory hungry will massively reduce the performance of that machine. And also, the secret that no one wants you to know is that you don't have to scale, because adding more power goes a really long way. You can get incredibly far in site size by just adding more powerful servers to your database cluster. Like, the sort of servers you can get now, especially on the cloud, are so incredibly, ridiculously powerful. And generally, especially Postgres, scales quite well with the number of cores and memory it has. You don't have to try and make a fully sharded sort of self-healing set quite as fast as you think. In particular, read-only replicas are a great first step, where you basically have sort of, you know, you have a master and followers, and then all you have to do is just, okay, we'll move all of our read queries to the followers, and then every so often, when somebody writes to the main one, we just pin them there for a while. It's a very well-known technique called pinning. Look it up. It's very cheap to do. We use Eventbrite with great success. Now, the one thing here is, of course, the final thing, you will need to scale. There are, in this one, I've got 4 basic ways you would scale and how to prepare for them. There are other ways. Don't take my advice as verboten, but here we go. So first of all, sharding points. It's always helpful if you think you'll need sharding to think how you would do it. In particular, sharding datasets, for those who aren't familiar, is taking a single table with many, many millions of rows and then splitting it into the same table on multiple servers, but which server it's on is determined by some well-known algorithm. So usually it's either consistent hashing, where a primary key of the object is run through a consistent hash function, which always outputs a number from 1 to n, and that's the server you choose. Or it is something like a lookup table, where you have a second table with primary key, shard it's on, and then you look up in that table and go off to it. Both of these are valid. They have different sort of access patterns and uses. But think about which one you might want. It especially depends on the sort of the clustering and groupiness of your data queried together. And then make sure that, for example, you have primary keys that could support this properly. One of the best things is having primary keys that are properly random strings rather than incrementing integers helps us a lot. It doesn't have to be true, but it can help a lot. Another thing there is also you want to basically, when you make your initial sharding set, don't have that 1 to n function output like 2. It's like, oh, it goes on A or B. Have it output 4096, and then say the first 2048 are this server, and these ones are this server, and then it turns out you can migrate much easily after that. Vertical split. This is when you have 3 or 4 big tables on your database, and you want to lessen the load, and they're all being accessed pretty heavily. For example, at Eventbrite, we have things like a users table and an events table. These are obviously both very popular. And so one of the things you can do is move them onto separate database systems or clusters or even to single machines. And that way you move the load away from each other, and these 2 heavy tables no longer conflict with each other, no longer overwrite each other's kind of memory space and that kind of thing. Denormalization is a very good technique. This is where you write things that are through the other side of joins into the table you're joining from. For example, if you have a forum posts table, you may denormalize the username of the posting user in there. So when you try and render a forum post, you can just get all the data for that single rendering from one row in the forum post table. It's not free. What it does is slow down inserts and updates, because every time you insert, update a row, you have to go and insert, update it everywhere else it might appear. So bear in mind, if you're read heavy, as we'll see later, this comes into play, that's a very good idea. If you're write heavy, it's a really bad idea. Don't do it. And finally, consistency. Now, one of the big things, and this is a big point I want to push, is that if your product design, if your website can take inconsistent data, if your users will happily take it, then you have this magical superpower where you can use inconsistent data stores, or at least not fully consistent ones. This is very, very dependent on the website and the product you're doing. For example, Eventbrite, we sell tickets. We can't be inconsistent with those, because we can't say, there's 5 left, there's -3 left, there's 2 left. That's not going to work. We have to have this very perfect data store. But other sites, for example, ones with like just social sharing sites, for example, It's not important the exact order your tweets appear in, for example, just that they're roughly correct. And so they can get away with a little bit of stuff there. So sort of bear that in mind, and if you think you can design your product around it, make sure you set expectations up front and go to people and sort of perhaps even build an inconsistency from the start so users aren't suddenly surprised when things are out of order. And this sort of comes on to the idea of load shapes. Now this is sort of this is a triangle. Here it is, a triangle. And this is a very basic sort of way of illustrating the different kinds of database storage there are. People always think there's one true kind of storage for databases. It's this big data, wonderful thing. That's not true. Depending where you are on this triangle, and this should really be 4-dimensional, but I can't project that very well, so we'll go with 3. Also 2-dimensional even. You sort of have different needs. And in particular, like different kinds of sites and different kinds of applications fall in different places. So some things are very read-heavy, as it's set up here. For example, a TV show website is deployed to once and probably never touched ever again in its lifetime. I've written some, I know. And so, you deploy the website and then it sits there for 3 decades, hopefully, and no one ever updates it, just fixed in time. Those are incredibly easy to do, so we'll come in a second. Things like Wikipedia, they're pretty read-heavy and they're pretty large, but there's also, there is some writes, but compared to the overall volume of Wikipedia, that's not that much of the traffic. It's mostly people trying to read stuff and put it into their essays. And so here it sort of sits halfway between large and read-heavy here, where like it has to be available all the time, and it has to be sort of seen to a lot. But like, if somebody writes a new article, we can wait 10 seconds to put it up. It's not that important. Large size, and then neither of these is very sort of archivable. So Amazon Glacier is a good example of that. They're a service where they will store stuff basically not online for you, and then if you want it, it takes a couple of hours to come back. It's probably on archival media somewhere. And then 2 sites I've worked on here, Minecraft forums, which at least used to be a bit smaller now, but used to be very, very popular. As a forum, it's both very read and write heavy and also quite large. It sits in this annoying middle section here. There's no real right answer. And similarly, Eventbrite is a bit larger and a bit more write heavy than that. But still, we have a lot of, especially when there's a sort of a new event going on sale, there's a lot of read. A lot of traffic comes to that page going, we want to buy tickets. And that first hit is a read going, how many tickets do we have? Can we sell them something? That kind of stuff. And this kind of sits in like different kinds of solutions. This is a very simplistic idea, but this is kind of how you could visualize like the different kinds of solutions fitting into there. So right up here, where things are really read heavy, you have this, it's flat files, it's in-memory cache, it's very simple. Like Nginx can just serve this stuff for you properly. That's very simple to deal with. Over here, as I said, offline storage, Amazon Glacier, just hard drives, and wait till the end, because there's an interesting revelation about that, could be used. And then over here with write-heavy, which I had as a logging example in the previous slide, that's very different. A write-heavy load is quite difficult to do. Generally, you want to sacrifice some of your ordering here as well. But there are certain append-only formats that work very well with that. And in fact, there's some native support in Linux kernels for appending. But they're very tricky to do. Like having a high-throughput logging server, it's difficult. And then sort of in the middle here, you have this sort of, here I've written as indexes, but also it could be different, like relational versus document, that kind of thing. Like you have to sort of make an educated decision on what kind of load do we have. Like obviously the more indexes you have, the slower writes get. And the fewer indexes you have, the slower reads get. So it's this balancing act here of like, where do you want to sit on that spectrum? And as you get bigger, of course, the indexes get bigger. And so even if you have this, 100 terabyte data set, adding indexes can make it 200 terabytes, so there's too many indexes. You're really aware of that. Finally, I want to cover some extremes. These are some interesting storage challenges that I want you to go away and think about. So first of all, the very sort of extreme points of that triangle there, extreme reads, extreme writes, and extreme size. Now, each of these comes with a trade-off. If you're very, very heavy reads, then you can get away with lots of replication, lots of caching, lots of sort of very slow invalidation kind of stuff. If you're extreme writes, as I said, you can sacrifice audio consistency because you probably want that. Like, usually in that scenario, you're logging data from experiments or logging from servers, something you want to have all of it. In that case, you can sacrifice some of your ordering or some of your consistency. Or in logging, you can sacrifice about 10% of the messages, as long as they're a random 10%. And in extreme size, you have to sacrifice query time. You're not going to have a big data set that's completely online and queryable unless you are Google and build your own data center, and we can't all afford that. But some interesting other ones are these three. So extreme survivability. What if your goal is a data store that can survive any kind of condition? Say you're building, I don't know, a space probe. You know, Voyager has spent decades and decades in the outer solar system being bombarded with radiation, and it still works. It turns out what it has is rad-hardened flash memory, and occasionally one of the flash cells gets hit by a cosmic ray, and they reprogram it from Earth over the solar system and sort of turn off all the bad memory cells as they go, which is incredible. One of the other things you can have is extreme auditability. This is what banks should do, but they don't. This is the idea of true append-only storage. Now, some companies make storage that can physically only be written to once, often flash memory or things like tape or whatever, that like once you've written to the track, you physically can't change it. In fact, CDRs and DVDRs are one of these true formats where you can write once and then it never be touched again. But they're not very good to stream to those. But the final one I want to leave you with a thought on is extreme longevity. Now, how many of you do backups onto hard drives or SSDs? It's a rough raise of hands. Well, a couple. So here is a list of how long data lasts on each of those formats. Turns out SSDs, if you unplug them and leave them on the shelf, after 3 or 6 months, data will be gone. SSDs are incredibly bad at data retention. You should never trust them for backups. Please be aware of this, because I know I have done this before, and it's not. You might be lucky, but the more modern and the more enterprise and the more writes they support, the faster they degrade. Consumer flash drive, like the USB pen drive in my pocket, CDs, DVDs, they last about 3 or 5 years. After that time, the CD will start peeling away and the ink won't be readable properly anymore. Magnetic tape and hard drives, they're pretty good, 5 to 10 years, give or take. If you store them really well, the tape will last a lot longer, but tape is quite fragile. Similarly, hard drive platters will last a long time, but the mechanics of the hard drive itself fail after a while. So your problem there is not the data, it's the mechanism to read the data back again. But interestingly, there's some good research here. You can buy a long-life flash that lasts for over 100 years. The colder it is, the longer it lasts. So in particular, if you freeze this flash, I think it lasts over 200 years, which is pretty great. And there's also people making basically metal carbon DVDRs that have this ridiculous composite format, and they're meant to be lasting similar lengths of time. So if you ever want that kind of longevity, if you're a long now project, good kind of research area. But finally, a few getting points. First of all, big data isn't one thing. It depends on your size, your complexity, your latency. Take your problem, look at it, work out the best thing for you, and don't just go towards whatever's popular, whatever's like easy, but do consider your team's strengths. Like, don't pick a brand new thing you're unfamiliar with when the thing you're all familiar with is only slightly worse, but obviously you can write it much quicker. Focus on your current problems. Don't focus on, well, when we're big, we'll have all these problems and design for those. Focus on your ones now. This is kind of a very important thing for small companies. If you focus on the big problems, you'll never solve the current ones, and it won't work well. Efficiency and fast iteration matters. Your database is part of this. Your storage is part of this. Don't be bogged down by that. And finally, a very important thing, good architecture for data affects product. Don't have this sort of design where you design the product and then we design something to back it. The best kind of sites take their limitations and their problems of their storage and take it back to the product and make a few subtle changes that makes it a bit better. For example, if you get like, well, we could store things a lot better if we didn't have to show posts immediately and waited like a minute. If that's the thing you could feed back into the product, and then that solves your storage problems, that's even better. And it's this wonderful virtuous cycle of both working together to make sure that you have a great storage and a great site. And for that, thank you very much.
Thank you very much for this great talk, Andy. And let's start the discussion. Okay, come on, children, don't be shy. Sorry, wait for the microphone, please.
Sorry, yeah. You said something that something exciting is coming about the glacier.
No, I was mentioning that it just happened.
Okay. I thought that there's something interesting happening in there because it's not really like extremely interesting technology.
No. It's,
so, okay.
I mean, it's interesting how they're doing it, perhaps, but yeah, it's more that having a widely commercially available cold storage solution is interesting, but not very important unless you're a bigger site,
sure,
basically.
Okay.
Yeah.
Hi, thank you for the interesting talk. I'd like to get back to one of the first slides that you had on your presentation. Where in that slide would Eventbrite be?
Which
the
slide
one
is
with
that?
with the rows, 1,000 rows, 1,000,000 rows, 10 million rows.
So I'm not allowed to disclose,
I thought so.
unfortunately. One of the rules we not, unless it's very large. I'll say that much. Yeah, we have a very big data set, but I'm not allowed to give out exact numbers for reasons.
Yeah, sure.
Sorry.
Okay.
Hi, thank you for a great talk. And I wanted to ask about those techniques that you said about the normalization database and other stuff. Isn't it better than use that a little bit unnatural techniques, and instead of that use just NoSQL databases and just proper database for your purposes?
Yeah, so I mean, so a NoSQL database, or I call them non-relational, they are kind of they're denormalized by design. One of the problems is that you can't have a mixture. So especially something like Mongo, if you want to do a join, you can't. It's like, you know, a relational database is very good at doing joins. It can optimize joins and eliminate all the rows that aren't there very quickly using algorithms and stuff. In a dumb NoSQL store, if everything is denormalized, that's great. If you want some things denormalized and some things fully relational, you can't have that combination. And so I'm a big proponent of a data store like Postgres that has very good NoSQL querying. For example, you can index into JSON fields in Postgres now, and also has good joins when you want them. Like, you know, Postgres will join through 3 tables without too much sweat, but it'll also happily index through like 3 levels deep into a JSON blob for you. So having that balance is my preferred thing. But yeah, if you have a solution that you know is fully denormalizable, then NoSQL is fine. It just depends on your situation. Thank you.
I wanted to ask which are most popular mistakes when planning data migrations? Let's say newbie mistakes that could be avoided easily.
That's an interesting one. New mistakes. I think the most common mistake is assuming it runs quickly. Most people I've seen will design a migration in development where they've got, say, 100 rows in their development database. I'm like, oh, it works perfectly fine. And it takes 4 hours in production. Another one I've commonly seen is people not expecting crazy data. So I once had a data set with latitude, longitude rows. And I tested it locally, it was perfectly fine. Turns out the real site had latitude, longitude, but also had, I forget the projection name, it's a United Kingdom specific projection where we try to resolve numbers, they tend to be off the top of the North Pole. So you've got to be prepared for invalid data sets in production, and all manner of things can go wrong. So it's more defensive programming, I guess, is what I'd say to be important about.
Hi, thank you firstly for Django migrations.
No problem.
I want to ask you about migrating the data from MySQL to Postgres that you talk about.
Yes.
How big was data set and how long it took?
So that one, I forget, I think it was about 60, 70 gigabytes in the end. The initial version I wrote took 12 or 13 hours. In the end, it took 30 minutes. Thanks to the optimization. The type ones particularly dropped down most that way. So it's about 30 minutes for about 50, 60 gigabytes. And the advantage there is we turned the old MySQL thing into a read-only site, which Lanyrd had that mode in it. And that let us transfer and start the process while serving read-only content, and then we cut over to the new thing once it had been transferred. So there was no actual downtime, just about half an hour, well, about an hour or so in the end of read-only mode, because half an hour transfer and then half an hour of us verifying the content was correct. In development, there are issues with like the quoting was weird and that kind of stuff. If you're interested, the code for that is up on Lanyrd's GitHub account. You can just go there and find it. It's got a few changes and improvements since then. I don't really maintain it, but it's there if you're, as a good starting point if you're interested in that kind of migration yourself.
Thank you.
Thank you.
Hey, you said that you can have tables in 2 different databases, right?
Yes.
So how do you, have you done this, and how this does the relations and how this works out actually?
Yeah, so in fact we're doing this right now at Eventbrite. One of the things we're doing is moving from a big single monolithic database to lots of small ones, as we're making a sort of more service-oriented site as well. And one of the problems is, as you mentioned, you can't have foreign keys across different databases, and maintaining integrity of foreign keys is now the job of the application. So Now we have code that if you send something to a service, it calls the thing with the other table and says, is this event ID valid? And the thing is yes, and then it saves it. So that's kind of done then. And also you can't do joins properly. So there's a different kind of approach there where you start doing essentially forced denormalization and forced joins in software. And we're sort of developing ways around that. So we have a thing called expansions now internally, where you can take a set of results from, say, our event service and say, okay, I want to add all the different ticket classes that these things have onto these events. And even though that's a separate set of tables and database queries, our code will correctly parallelize or optimize that to other servers. It's kind of like moving down those joins one layer down. That's probably not necessary for most small sites, and there are data stores that do this as well, and claim to this themselves as well. But that's one thing we're doing.
Okay, but do you use relational databases or?
Yeah. MySQL all the way for us. Not my choice, but we have good MySQL DBAs, so that's why.
Okay, thanks.
Right here.
Oh,
I have a question about the triangle and data used for graphing. What would you do with that? It's kind of write heavy because a lot of data comes in and you only want to put it in a graph every once in a while, but you want for it to come up immediately when you look at it.
Yeah.
Where would you categorize
when
that?
I said there should be more dimensions to this triangle, I did actually mean it should probably be at least 4-dimensional. But yeah, so it's like graphing is interesting because graphing is basically tends down sort of this level, right? It's very write heavy. You don't read it very much, and it's usually a large size. Now, obviously, if you can take the loss of accuracy, then an RRD kind of thing where you lose accuracy after certain time periods is great. Otherwise, you're going to end up with basically something that sits around here, where it's this large write-heavy thing with not very many indexes, and then probably batch jobs to bring data up to this section. So like, every couple of minutes, do a big batch query to bring something up to this level of storage where you can see it pretty quickly and easily.
If you know what to query for.
Yeah, exactly. If you know what to query for. If you don't know what to query for, then nothing will, you have to basically just say, invent your query, put it in, and then 3 minutes later it comes out. It's never soluble if you want all three of these, usually the fourth one is time. You just have to wait, right? It's one of those things.
All right, thanks.
Thank you.
Okay, hello. You mentioned that sometimes, here.
Oh, there you are. Sorry, it's very hard to see. There's lots of lights.
So you mentioned that sometimes a developer has a small database, like 1,000 rows or something, and has a migration, and it works well. And do you have some workflow of testing migrations of production-like database, to test if it, takes a few hours and...
So my recommendation there is to usually have a copy of production. So generally, if you're lucky enough to have, say, a read replica that you've already got, you can take that, make it its own small master, and then just try it on that one, because it'll have a copy of production. So, Eventbrite, we have tens and tens of read masters, and we can try one of those and throw them away and re-replicate them again. At Lanyard, again, we had a system where we could download the full dump of production from the previous night into our development machines and then spin that up and try it on that. Again, that was only tens of gigabytes, so it's possible at that point for us. But if you've only got a moderate size like that, you could have a system where not only is it that good, you're then testing your backups work too, because you're taking the backup, making it big to make sure backup works, and then trying the migration on it. So it's like a good through combination of all of those things. Okay.
I've done something like that, but I was not for every pull request, right?
No. This is most migrations you'd be like, oh well, this is obviously going to, it's adding a column, it'll work fine. It's the ones that we're changing the password hashing, right? Things like that. You would go, okay, we're going to try this one on everything, or we're changing from latitude, longitude to some other version of coordinates. All the things that have actual code translation in them are the ones I would test personally. Where because your Python code is probably the bit that's the most likely to fail, because databases are much better tested, and
data migration scripts, right?
Yeah, us migration writers aren't perfect by any means. So.
Okay, thank you.
Thank you.
You advised to wait with scalability sort of considerations. One of the things that tends to be complicated is when you rely on joins to work across the board, and suddenly you decide, oh, my data is too big for one server, and you start sharding. So how would you advise to approach this thing? Should we start with sharding from day one? Should we sacrifice some joins from day one? How would you do that?
So I still don't think for most companies it makes sense to try and not have joins from day one. Joins are a very useful feature, and especially when your schema is changing a lot, not having joins in there and having, like, say, denormalization is way worse for your, like, amount of changes you can make per thing. One good thing I like doing, though, is as you get bigger, start testing it, like, start deliberately trying that stuff, and then, you know, say, okay, like, what if we had to suddenly not join between users and events? What would happen? And then sort of perhaps plan it, perhaps try it out, but you're right that it is a big change you have to prepare for, but also at the same time, I don't think you should be doing this stuff from day one, because I think the overhead of that is, unless you know you're going to be big, like, you know, an internal Facebook project knows it will be big, so it can start like that, but something like, you know, a small startup perhaps doesn't know that as much, so I think it's a different kind of scenario for them.
Okay, I have another question. With recent Postgres additions, you can actually run Python code in the database kernel.
Oh, yes.
Versus first reading the data into Python and then processing it and writing it back. Do you have any experience with that? Is it faster to do things in the database kernel than actually getting the data out first and then doing the processing externally?
So I've played around with that. It is definitely faster because you're saving the network trip is the biggest part. Like, it's still, like, you know, deserializing data from storage, but you save usually 50 milliseconds per row or whatever of network. Especially if you're not batching, it's even quicker. The problem with that code is versioning it. That code does not live in version control. So generally, you need to have a very good system of migrations that are versioned, but version that code, and then you're usually fine. But yeah, like, it is a lot faster. There are things you can do badly. I once saw an example of someone had loaded Ginger into Postgres and was rendering their templates from the database. They just did select render template star from table, and then just HTML came back, which is impressive but terrifying at the same time.
Okay, thank you very much for the great talk, Andy.
Thank you.